Welcome back, everyone. In this video, we will be continuing the section on hyperbolic trig functions. Now, this video, we're just going to be talking about the derivatives. We don't really need to know or expect you to know a ton of things about the hyperbolic trig functions. You can use Desmos or your graphing calculator to graph them. If you ever need to graph in your calculator and you don't have hyperbolic trig function buttons, we talked about in the previous video, you just have to use their definition. However, the derivatives of these are the one example where we just use what we already know and we don't have to use the limit definition to figure them out. Why? Because the definition of, let's say, hyperbolic sine just involves e to the x and e to the negative x. And we know how to do the derivative of each part. If you're peeping below, then you'll notice that I already have all 6 written out for you. I don't want to talk about all 6 of them right now, but I want to go ahead and show you how you can arrive at this one. So the derivative of hyperbolic sine of x equals hyperbolic cosine of x. How can you arrive to that? Well, if we want to do the derivative of hyperbolic sine of x, want to make sure I don't put the h inside the parentheses. The definition of hyperbolic sine is that's the e to the x minus e to the negative x over 2. Now, if you were asked to do this derivative, we could have done this derivative the second we started talking about the chain rule. And you should be comfortable with doing the derivative of this by now. Don't feel overwhelmed just because we're kind of confirming a derivative rule. You know how to do the derivative of this. If it helps, you can bring the 2 out because it's in the denominator. It's really a 1/2. And then we do the derivative of e to the x minus e to the negative x. But to do the derivative of this, we do the derivative of each part because it's linked by a minus. The derivative of e to the x is just itself. And we have our minus. The derivative of e to the x, well, we got to use the chain rule there because it's not just x, it's negative x. We have the derivative of itself, so e to the negative x. Then we multiply by the derivative of the exponent. What's the derivative of negative x? That's just negative 1. Right, so hopefully you are pretty comfortable with what I just did. I hope so. And now you really only have 2 steps, and you can actually see that what we have here is hyperbolic cosine. You might already see it already, in which case that's awesome. But let's go ahead and simplify it a little more. Well, the e to the x in front, you can't do anything to, but this minus here, since it's getting multiplied by negative 1, it's really a plus e to the negative x. And now maybe you see why this is hyperbolic cosine, but if not, we can take this 1/2 and we can bring the 2 down to the bottom here. And we get e to the x plus e to the negative x all over 2. And this is the definition of hyperbolic cosine. And there you just proved a formula in calculus. If you followed along, you just proved a formula in calculus. Now you can go through and do the rest, but of course there's 5 more, and I think that for the most part that would be a waste of time. But one thing that's definitely for certain when it comes to the derivatives of, let's say, the tangent, the cosecant, secant, and cotangent, the hyperbolic ones, is that you use the definitions just like we would have in the previous section when we started talking about derivative of just trig functions, and you use the quotient rule. Now, as far as the 6 hyperbolic trig function derivatives go, the main thing is you just really need to memorize the 3 sine, cosine, and tangent hyperbolic. You can memorize the other 3, it doesn't hurt. I won't expect you to have these memorized, but these should be memorized. And the reason they should be memorized is really because they're the 3 that you would see pop up. These pop up maybe 1% of the time you actually deal with hyperbolic trig functions, and hyperbolic trig functions probably pop up 1% of the time you're dealing with any type of function. So it's very rare to see these. Now, one thing you'll notice is that the derivative formulas are extremely similar to the derivative formulas for the regular trig functions. Right? If you kind of ignored all the whether it's negative or not, the derivative of regular sine is cosine, the derivative of regular cosine is negative sine, the derivative of regular tangent is secant squared, and so on. The derivative of regular cosecant was cosecant cotangent with a negative. The derivative of secant was secant tangent, not negative. And the derivative of cotangent was negative cosecant squared. Pretty much if you ignore all the negative signs, it's exactly the same. It's just that the way the negative signs work with the hyperbolic trig functions is that for the main three, sine, cosine, and tangent hyperbolic, there's no negatives. For the other three, cosecant, secant, and cotangent, they all have negatives. So the way you can memorize whether it's negative or not is different, but otherwise the same as the regular trig functions. For the regular trig functions, the negatives were on the derivatives of the c functions. For this one, the negatives are on the quote-unquote other three, the not normal three. All right? But because I really only have an expectation of memorizing these three, we'll really only test you on these three. But they're just another tool that you have. Whether you're going to use the product rule, the chain rule, the quotient rule, use it with the power rule, anything like that. These are just new tools, just like all the other derivative formulas we got. Number 1 here says find the derivative of f of x equals e to the x times hyperbolic sine of x. Well, yeah, we have one of our new functions, but we're just going to start with doing the product rule. The f prime of x, the derivative using the product rule, the derivative of the first is just e to the x, multiplied by the second, which is just the hyperbolic sine of x, plus the first, which is e to the x, and then multiply by the derivative of hyperbolic sine of x. Because the inside's just x, we don't need to do the chain rule at all. It's just hyperbolic cosine of x. Right? That's the rule we actually derived, but we want to just use it like this. When you're talking about hyperbolic trig functions, you only use their definition to evaluate. Like if we wanted to do hyperbolic sine of 2, we would do it like we did in the previous video. But if we want to work with their formulas, we just want to use the actual names here. It's a lot easier to write down. Now this is it. We've actually done the derivative, but you could simplify it. If you were asked to do the second or third derivative, you would have to go further, and we know simplifying is a good idea. You can factor out the e to the x, and you get hyperbolic sine of x plus hyperbolic cosine of x. But that would be it. Number 2, we're asked to find the derivative of y equals hyperbolic tangent of x to the 2/3 plus 4. Well, to do the derivative, one thing to note here is there's no product or quotient at all, so we're just going to do the derivative. The inside's not just x, which means we're going to have to use the chain rule, but we know with the chain rule, we just start with our normal rule. What is the derivative of hyperbolic tangent? Well, if you don't have it memorized yet, just think about what's the derivative of tangent. It's secant squared. But because we're talking about hyperbolic, we want to do the hyperbolic one. So it's hyperbolic secant squared. We write the inside. We keep the inside the same. That's what the chain rule always tells us. But the additional chain rule step here would be to multiply by the derivative of the inside. We have to multiply by the derivative of the inside, x to the 2/3 plus 4. But once again, we're just implementing the chain rule with our new rule. As you can see, otherwise it's no different than anything. Really, if I ask you the derivative of this, which is tangent, pretty much would get exactly the same thing, except there wouldn't be an h here. Well, let's go ahead and finish it up. I'm going to rewrite the first part. And then the derivative of x to the 2/3 plus 4. Well, for the 2/3, we bring it down, x, and subtract 1 from the power. 2/3 minus 1 is negative 1/3. Now the derivative of 4 is just 0, so I can leave it like this. And if you want, you could leave it like this, but we talked about how it's undesirable to have negative exponents. So let's go ahead and just simplify it for a safe measure. The 2 here we can bring to the front. It's on the top. We have 2 secant squared, or sorry, hyperbolic secant squared of the inside x to 2/3 plus 4. And that's divided by, we have a 3 on the bottom, but also the x to the negative 1/3 when it goes to the bottom becomes x to the 1/3. So this would be the derivative completely simplified. Once again, nothing really wrong stopping here at all. but completely simplified, no exponents that are negative. This is as far as we're going to be able to take it. All right, so number 3, the final thing, I'll draw the picture because this isn't an obvious picture at all, but it says a telephone line hangs between 2 poles 14 meters apart in the shape of what's called the catenary. Now that's just the shape of something that has the hyperbolic cosine shape. And the way it looks like, you have a left pole here and a right pole here, and they are 14 meters apart. And what's happening is this telephone wire, it's not completely taut. So if you think about telephone wires, you've probably seen them, electricity wires on the side of the road or something. They're usually completely taut, but I guess this one has some extra drag in it or something, and it's not completely taut, so it dips down a little bit. So this is what we're talking about. Now it goes on from the left and from the right, so it repeats itself, but we only have to focus on this one. And the shape of this is given by this equation. What it wants us to do is we want to find the slope of this curve when it meets the right pole. Right, so the slope right here, we can just sort of visually estimate it. It looks like that because we know the slope at a point is the slope of the tangent line. So this is what we're looking for. And we know that means find the derivative and plug in the appropriate x value. Now, one thing you might have to be careful on is what you're going to plug in for x. Well, one thing that usually the way this is drawn, and this is given to you too, but I just didn't draw yet because it wasn't a part of what we were described, is usually these things are centered so that the middle of the shape, which is right here, is where the y-axis is. So let me go ahead and draw that. We have the y-axis right here. And then sort of the x-axis down here. This one is not as important to draw, but I'll draw it in anyway. So we have our x and y-axis, and we want the slope at this point. Well, the thing to think about here is when we figure out the slope, we know that we're going to get dy over dx. It's going to have an x in the formula, and we have to plug in an x value. What's the x value at this point? Well, the x value, since this whole thing is 14 and this is cutting it in half, this is at x equals 7. So once again, think about it. This is 14 wide. We have to go the same left and right to get to 14, which means it is 7. We go 7 to the right and 7 to the left to get to each side. So we're going to figure out the slope by doing the derivative and plug in x equals 7. All right, that's the first part. The second part is actually pretty interesting. It's not something we've talked about, but I don't want to talk about it yet because we're not there yet. All right, so part A here, we're going to do this exactly like we described. Find the derivative of our function. The derivative of our function here. We know that this minus 8 is going to go away. The derivative of 13, sometimes this hyperbolic cosine, the 13 sticks around. The derivative of hyperbolic cosine is just hyperbolic sine. Remember, it's not negative. The inside we rewrite as x over 13. And then by the chain rule, because this is not just x inside, we multiply by the derivative of the inside, the derivative of x over 13. Right? So let's just kind of go through that. Just because it's written up here, we're kind of focusing our eyes down here. When we do the derivative of this, we know because there's an x here, the 13 in front's going to just hang out. The derivative of hyperbolic cosine is hyperbolic sine. We rewrite the inside, and because the inside is not just x, we have to multiply by the derivative of the inside, which is x over 13. And then the derivative of 8 is 0, so don't have to add that in. Well, what's the derivative of x over 13? That's just 1 over 13, because the derivative of x is 1, we get 1 over 13. We have 13, hyperbolic sine. I'm going to write this x over 13 like this, so it's a little easier for us to read, times 1 over 13. Now this 13 is inside, it can't come outside, but this 13 is outside and it actually perfectly cancels with the other 13. And we get hyperbolic sine of x over 13. That is the derivative formula. Okay. Now we're asked for the slope of this curve, which we figured out already we need to figure out the derivative and then plug in x equals 7. So to answer this question, we want to take our dy over dx formula and plug in x equals 7. This is the evaluation bar. It just means take your formula, whatever's over here, and plug in x equals 7. We get hyperbolic sine of 7 over 13. Now, by definition, which is how you might have to do it if you don't want to use Wolfram Alpha or you want to use your own calculator, that's why I talked about in the previous part of the section. We have e to the x, e to the 7 over 13, minus e to the negative x, e to the negative 7 over 13, over 2. Let's go ahead and figure that out. And I didn't write how far to round it. The other problems we were rounding to 5 spots, so let's just do this one to 5 spots as well. We have hyperbolic sine of 7 over 13. Just see what that is. So it should be 0.56486. Let's just make sure it is by actually typing this in. E raised to the 7 divided by 13 minus e raised to the negative 7 divided by 13. I didn't start a parentheses, so let me go ahead and do that. And then divide that by 2. Yeah, that's exactly what we had. So hyperbolic sine 0.56486 is our answer. 0.56486. Right, that is the slope at this point. Now the other thing we want to do is find the angle between the line and the pole. This isn't something we've done before. We haven't talked about angles related to slope, but we'll see very quickly that it's just really related to sine. The reason is this picture here, what it's talking about in the picture is this is our theta. So the pole is here, we have our slope here, and we want this angle. How do you figure out that angle? Well, the thing is, you know the slope, and if you kind of complete a right triangle here by drawing this line, slope is y over x. So that means the y value, you can think about it as being the 0.56486, and x, the x value here is just 1. Now, not necessarily drawn the scale. Let me emphasize that. It's not necessarily drawn the scale. But if I go ahead and blow up this triangle on the right here, just to make it a little easier to see, this is our theta. Our y value is, we can always think of the y value when we're talking about the slope as just the slope itself, 0.56486. And then the x value is 1, because slope is basically y over x. If we divide something by 1, we get itself back. Well, if you want to figure out this angle, this is probably one of the first times we're really using trig in this course, besides some identities and stuff. But you can solve for theta because we can set up an equation. Tangent is opposite over adjacent. The tangent of theta, notice that this is the actual trig functions, no h. Tangent of theta is opposite 1 over adjacent 0.56486. And hopefully you remember how to solve this. Tangent on one side becomes tan inverse or arctan on the other. So we got arctan of 1 over 0.56486. And let's just pretend we want the angle in degrees because that makes sense. We want to interpret this angle. If we get it in radians, it might not make a lot of sense. Well, in order to do this, we've got to use a calculator. We cannot do this by hand. Well, I always write arctan in this calculator, or arc whatever trig function is, but you can write tan to the negative 1 power as well. We have 1 divided by 0.56486. And now one thing that Wolfram Alpha always does when you initially type it in, it's in radians. So if you want degrees, you'll either have to take the answer in radians or see what it writes in degrees. It doesn't always convert it, but this one converted to us. So theta is 60.54 degrees. And that would actually be the answer. All right, a little heavy-handed, I know. We haven't really talked about angles dealing with slope before. But the point is, if you figure out the slope, you can always make a little triangle like this. And depending on what angle you want to figure out, the one that is in our picture is the one that happens to be drawn up here. We can figure it out like that. But if we wanted this angle, for some reason, maybe our picture indicated we wanted this angle, we would still have the same y and x values. We would just set up our equation differently. But I'm going to go ahead and erase that because that's not actually what we were asked for to do. And I just rounded 2 spots because Wolfram Alpha did, but for interpretation reasons, I think that's plenty good. You know, if you want to figure out this angle, if you know that it's about 60 degrees, you can roughly see a picture in your head of how big 60 degrees is, and that's really what you're going for. All right, so we're pretty much done. I can officially say that after this section, we are completely done with derivative rules. I know I've been saying for a few sections, we just have to add in a couple techniques. Over the last few sections, we've really talked about the inverse trig functions and the natural log derivative rules. And then we saw last section with logarithmic differentiation. We added in not really a rule, but we could do the derivative of something like x to the x. Well, at this point, you know all the derivative rules. I know. I do not know a single one that you don't know at this point. Right? So just to summarize, the main properties we know how to do the derivatives with additions, subtractions, multiplications, and divisions. Right? These two properties, they just break it up. We have to use the product rule for multiplication and division, the quotient rule. We know how to do the derivative of just x, just a number. This stuff was pretty much the first section, and then we introduced the power rule, x to the n. We also introduced derivative of e to the x. Then after that, we started talking about the derivative of trig functions. And we also then added inverse trig functions. And then the log and other exponential functions, but mainly ln of x. Then at some point, we added in the chain rule, which told us how to do all of these rules, but if the inside is not just x. So if we had something that wasn't x here, how do we do it? Right, and then pretty much our last two things were techniques. We talked about implicit differentiation and logarithmic differentiation. And probably one of the main things you want to take from logarithmic differentiation is not necessarily any specific rules, although we did figure out how to do the derivative of something like x to the x, but mainly what it's used for. Doing derivatives of something like this, you have to use logarithmic differentiation. But at this point, if we hadn't talked about this section, you'd pretty much be covered as far as all the derivative rules. This section just really completes the whole thing. Now you know all the derivative rules I know. You know the derivative rules of the hyperbolic trig functions. And once again, I'll continue to write trig in parentheses, but I think it just makes sense to say hyperbolic trig functions just because of their names. But ultimately, yeah, we learned a ton of derivative rules, tons of sections, tons of videos, tons of problems at this point, just talking about derivative rules and their techniques, but we know pretty much everything there is to know about derivative rules now. Now, going forward, we'll finally start talking about applications in certain types of problems. The big one next being related rates. But I will see you in the next section.